Here we're going to take a look at crystallization in the eutectic system, diopside plus anorthite. In an earlier video, we took a look at melting. Here we're going to pick up on the idea of interpreting this diagram, but we're going to take a bulk composition. We'll do something different than what we did in the melting video, where we're going to start at a very high temperature, something above this liquidus curve here. There's another liquidus curve over here that separates diopside from liquid. And we're going to look at what happens if we cool the system. So let's take a system here where the composition is 70% anorthite or 30 weight percent diopside. So if we take this system and melt it completely, we would have a liquid at some temperature up here. As we cool the system, we would follow the system down. Let's just track the entire history qualitatively. We'll hit the liquidus, then we'll enter this anorthite plus liquid field here. That means anorthite should be the first crystal to form. And then we'll hit the diopside plus anorthite field here. That means diopside will begin to crystallize at this temperature, the eutectic temperature of 1274. And then anything below that, we're out of liquid, no more liquid is left, and we simply have a rock, and that rock will get cooler as we withdraw heat. What is the temperature at which the first crystal forms? Well, as we move downwards on that bulk composition, we hit the liquidus right there. So it looks like it's right about 1450, maybe 1452 degrees centigrade. It looks like it's a tad above that hash mark there. And if we continue cooling, notice that if we take a look at this lever here, we have all liquid except for maybe just an infinitesimal amount of solids. How would we interpret the solid composition? Well, there's no solid solution. So if we trace this line across, our solid is pure anorthite. And as we drop the temperature, we trace this line across. And again, this curve, this vertical line here that acts as an axis is also kind of like a solidus. You can think of the solidus as being this horizontal line here at 1274, but the 1274 solidus line makes a vertical trend upwards up to 1553. So we have constant composition crystals. Notice here, this is the crystal side of the lever. As we decrease in temperature, the liquid side is fixed, but the solid side grows. So we get more and more anorthite. We're always in the anorthite liquid field until we finally hit 1274. That's when we finally get the first crystals of diopside to form. So now diopside begins to precipitate from the liquid. If we continue to withdraw heat, the temperature will stay fixed. All of the heat that we withdraw from the system, all of that thermal energy that is withdrawn will all go into converting liquid into crystals. Diopside and anorthite will crystallize together, and they will crystallize in a proportion that's equal to that eutectic proportion there. And so something close to about 42 weight percent anorthite, and then the rest being diopside crystals that are forming. And as those crystals begin to precipitate together at a certain point, the liquid will vanish. The last liquid composition will be of that eutectic composition. And if we withdraw any further heat, our bulk composition comes back over here once it's completely crystallized, right? We took a liquid up here and we crystallized it completely. And so when we do that, we maintain the bulk composition, and this bulk composition simply gets colder. What would happen if we have something over here, 20% anorthite, 80% diopside? As we begin to cool the liquid, the first crystal that we will form will be diopside. It will continue to cool down to 1274, where we would form the first anorthite crystals. And the system will sit at 1274 until it's completely crystalline, and then the rock, which will be a mix of these two minerals, will simply get cooler. What would be the temperature of the first crystals? They would be forming at about 1350 degrees centigrade. And from 1350 down to 1274, diopside is the only crystal we would make. And then at 1274, that's when anorthite would come in. As this is happening, the liquid composition is going to migrate down this curve. So if we start creating, if we have a bulk composition here and we create crystals over here, we're pulling diopside out of the liquid, and that's going to force the liquid to become anorthite rich. So the liquids will migrate down this curve until they hit the eutectic. So the very last liquids that we would have that composition, and that would go for the same example that we had over here. So we started over here in our other example where we make anorthite crystals. If we draw anorthite out of the system, then the liquid gets forced to the left. It becomes more diopside rich because anorthite is being subtracted out of it. And the liquid would follow this liquidus curve until the very last liquids we would have are at the eutectic. Notice that no matter where we start, no matter how anorthite rich or diopside rich, during equilibrium crystallization, all liquids end up here at the eutectic. That'll always be the last liquid that will form during cooling and crystallization. And then when the system is below 1274, it really doesn't matter what bulk composition we have. Below 1274, we have a rock. And no matter how much, whatever the proportion is of anorthite and diopside are, it'll always be a rock below 1274 in this very simple system. And below 1274, that rock will simply become cooler.